Hello class, welcome to today's lesson in which we're going to talk about some application of functions. We're going to have this lesson probably 2 or 3 times more, and so I'm gonna call this application of functions 1. Remember that the topic 2 is all about functions, and we have already spent quite a long time going over this mathematical concept, and now we're going to apply it heavily. Okay, so let's start. First, what I want to tell you is the following. Why are functions so important in mathematics? Okay, why do we devote it? Why are functions so important? Why did we devote so much time to the study of this mathematical concept, functions? What's so special about this concept? What's special about this concept, guys, is that basically we live in a world of cause and effect. Okay, if you look around, you will see that many quantities, I mean, first of all, there are many quantities in life, right? We have our weight, our height, our income, the amount of energy that the sun gives us per day, the number of atoms in a chemical solution. There are many quantities. Okay, the amount of quantities is probably infinite. And so there are relationships about those quantities. Okay, there's always in classical physics, there's a relationship of cause and effect, or in other words, there's a relationship of dependency. Okay, some quantities depend on other quantities, and when that happens, when some quantity one depends on a quantity two, we say that the quantity one is a function. That's how we mathematicians say it. The quantity one is a function of the quantity two. And you already know many types of functions. Even though you may not be aware of that, you know it. Intuitively, you know it. For example, let me give you some examples of these things I'm telling you. What examples of functions do we have in real life? For example, consider that the quantity demanded of a product. Think about cell phones, maybe. Okay, you have cell phones. I don't know. This is supposed to be a cell phone, and we know that objects or products that are more expensive will get less demanded, right? So, for example, if we try to graph the dependency of the quantity demanded of, in this case, cell phones, I'm gonna plot in here quantity demanded, and in here I'm gonna put the price of the cell phone. Then we have an intuitive understanding that as the price is cheaper, so as the price is more closer to zero, right? The quantity demanded of such product will be higher, right? Because people like cheap stuff. Okay, and as the price of this product rises, we're gonna get less demand of such object, right? So we know that this happens in real life, and basically what we are stating is that the quantity demanded of a certain product is a function of its price. This is how mathematicians say it. The quantity demanded of a certain product is or is equal to a function of its price. In other words, the quantity demanded depends on the price of such object. In what exact way, we may know, we may not know, but we know that it is a function. You see, there is a relationship for a specific price of a certain product. We may get certain quantity demanded. For another price of the product, you may get another, well, you will get another quantity demanded, and so on. So that's how this works. Let me erase everything. What other examples do we have? What about this? Life expectancy depending on income, okay, on how much money you make. I don't know if you knew about this, but this is true, guys. The more income you get in adult life, the more you are expected to live, which makes sense, right? If you make more money, you have more access to medicine, to better food, to better housing, whatever. So you are expected to live more. So if we notice this, if we can say this, we basically are saying that life expectancy is a function of income. You see, this is the way I'm capturing all of this sentence, which is in natural language, in this mathematical symbology, which we have used already. You remember? Okay, let me give you a taste of that. How exactly does it depend, though? Look at this graph from Harvard Gazette. It's a magazine. So household income and expected age at death for 40-year-olds. So as your income increases, you are expected to live more and more and more and more, even up into your 90s. And by the way, women tend to live more than men. Why is that, guys? Any ideas? Okay, so we say that life expectancy is a function of income, or in other words, life expectancy depends on income. That's another type of function. Another example. I always do this. Temperature. I don't know if you knew this fact. This is a very cool fact. One of the most impressive ones I know. The temperature, the ambient temperature, okay, the room temperature or the outside temperature depends. Some people have found that you can actually calculate the temperature depends on the number of chirps of crickets outside, like when you are in a, in the wild or something. Uh, so chirps. What is a chirp? It's when the cricket goes like that little sound that they do, los grillos. So if you count the number of chirps of a certain cricket, which is outside, you can actually measure the ambient temperature outside by doing this, guys, by counting the number of chirps in a certain amount of time. It's incredible.
Crickets, and the formula that you use according to the old Farmer's Almanac is that you count the number of cricket chirps in 14 seconds and then you add the number 40 to that.
Alright, we've got it set to 14 seconds and we're going to give it a try. Okay, it sounded like it was 39 chirps, and 39, and you add a 40 to that, you get 79 degrees, and the phone is showing that it is 81 degrees, so pretty close.
And for Celsius, what you need to do is you need to count the chirps in 25 seconds, divide that number by 3, and then add 4.
Okay, we're going to give it a try for Celsius. Alright, that was 67 if I counted right, and if you divide 66 by 3 you get 22, and you add 4, and when you get 26, and it looks like it says it's 27 degrees, so pretty close again.
So as you could see, the temperature outside is a function of the number of chirps. I'm going to represent that by this symbol, NC, number of chirps, of a certain cricket. And such function is defined by the following equation. The f of NC is equal to NC over 3 plus 4. Okay, so if you want to calculate the temperature, and remember that this is the temperature outside, if you want to calculate it, just count the number of chirps in 25 seconds, divide it over 3, and add 4. And you will get a pretty good estimate of the temperature outside. This is true, guys. This has been known for quite a long time. And it's got to do with the crickets being cold-blooded and some chemical reactions in their legs and so on, because you know, those things make those sounds, the chirps. I think they make it by rubbing their legs, and you know, there are very complicated chemical reactions going on in this organism, and I don't know how many legs these guys have. Basically, uh, temperature is affected by no, sorry, the number of chirps is affected by the temperature outside. So by just counting the number of chirps that these guys produce in a certain amount of time, you can calculate the temperature. It's pretty cool. And in physics, what do we have? For example, the velocity of sound depends on temperature. Okay, one more time, temperature. We have this quantity again. The more temperature you have outside, the greater the velocity of sound will be. And again, physicists have discovered that this dependency can be written in this way. The velocity of sound is a function of temperature, and such function has been nailed down very accurately as 331 plus 0.6 time temperature measured in Celsius. Okay, so being this the velocity of sound, you can calculate the velocity of sound as a function of temperature. You put the temperature in there, the temperature of the ambient, and you're gonna get the velocity, the corresponding velocity of sound. So this is your input, this is your output. So the colder it gets, the less fast that sound travels, and so on. You know, I could go on with thousands and thousands and thousands of functions in real life. Okay, you live in a world of functions. The dependency of one quantity upon another is one of the most impressive facts about the universe, but that's how it works. We live in a universe in which there is this kind of dependency, and that makes the universe understandable because we can relate quantities. Okay, if this was not the case, if nothing was related to any other thing, just try to imagine how chaotic that universe would be. Okay, probably intelligence would not even have appeared in such universe. It would be a very strange universe. So thankfully we live in this one. So the first thing I'm gonna show you how to perform, guys, or how to apply your knowledge to functions already, is we're gonna do this. We're gonna find the coordinates of the vertex of the graph of mistake of a quadratic function. Okay, I need to be more specific, of a quadratic function. So basically we want to find the coordinates of the vertex of a parabola. That's what we're going to do right now. I'm going to give you 3 examples of applications. This is going to be the first one. Okay, so let's do it. first thing I need you to understand, imagine that I give you the x-axis. We have the 0 here, the origin. 1, 2, 3, 4, 5, 6, 7, 8. Let's go up to 8 in the number line. And I'm going to put the number 4 in here too. Okay, first question. How can I find, for example, if you consider these 2 points, the point 4 and the point at 8, how do you find what number is right in the middle of these two? Okay, you have 4, you have 8. This number, I mean, we know it's going to be 6, right? But how can we come up with a formula to find such number, whatever these points are? If you notice, this number being in the middle of these two is going to be the average between 4 and 8 in this case. Okay, so the average, which is going to be this number, is defined as the sum of those two numbers over 2, right? Let's see if it works. The average, 4 plus 8, 12 over 2. So that is in fact 6, right? As we expected. There it is. So if I give you another two numbers, whatever numbers I give you, let's suppose I give you the number 3 and the number 147. Okay, if I tell you what is the point in the middle of these two numbers, right there, what is this point? What is that number? All you have to do is get the average between 3 and 147. In other words, you have to add them and then divide over 2. So it's going to be 150 over 2, which is 75. So this number right in the middle is 75, and we know how to find it. Okay, so keep that in mind. Okay, so let's find the coordinates of a quadratic function. And I'm going to do it in a very specific case. I'm not going to go over the general case for time reasons, as I always tell you. I can only give you some taste of how demonstrations go about, but unfortunately I cannot give you the whole detail. So let's consider this function, and let's consider that when I graph this function, my quadratic function, what I get is this parabola that crosses the x-axis at this point, x1, and at this point, x2. Let's locate the vertex. This is the vertex, and remember, what we want to find is the coordinates, the x-coordinate and the y-coordinate of this vertex, this one. And all we know is the x-intercepts of my function. Now, what are those x-intercepts? They're the zeros, right? The zeros of this function. Remember, the zeros or the roots. And if you remember, we can get those zeros by applying the general formula. 1 0 will be minus b minus the square root of b squared minus 4ac over 2a. That's going to be one of my zeros, or one of my roots. And the other one will be minus b plus the same radical over 2a. Now, for simplicity reasons, I'm going to just call this d for discriminant. You remember, this thing was called the discriminant, all that expression. Okay, so so x1 is equal to all of this and x2 is equal to all of this. Okay, and those are these two numbers. Now, the question here is this: how can we find, if you notice, the vertex, since the parabola is symmetrical with respect to the vertex, we expect this distance and this distance to be the same, right? Even though I didn't draw it very well, you know what I mean. The vertex is the symmetrical point in the parabola. Okay, the straight line, the vertical line, this one that goes through the vertex, divides the parabola in half. So basically we expect this point to be in the middle of x1 and x2. This distance and this distance are the same. Okay, so basically my question is this, guys: how can we calculate the x-coordinate of this point? This point, don't even look at this point yet. This point, the x-coordinate of this point. We have to get the average between x1 and x2. Do we know how much x1 is? Yes, it's this much. Do we know how much x2 is? Yes, it's this much. So let's get the average between these two quantities. So the average, which is going to be this point here, will be the sum of those two numbers over 2. And let's carry out the process. So x1 will be all of this minus b minus the square root of the discriminant over 2a plus x2, which is all of this, minus b plus the square root of the discriminant over 2a, and all of this over 2. Okay, now let's continue. The average is going to be minus b minus the square root of d minus b plus the square root of d over 2a. Since these two fractions have the same denominator, I'm putting them as a single fraction. You see, I'm actually performing the sum. And all of that over 2. So how can we simplify this fraction? We have minus the square root of d and plus the square root of d. So basically we have this minus b over 2a, because this one and this one got cancelled. They add up to 0. So we have this over 2. Let's continue. Minus b, we have minus 2b over 2a. All of that over 2, which can be written as 2 over 1. Let's divide this fraction over this fraction, and we're gonna get minus 2b over 4a. And when we simplify this, we get minus b over 2a. And I'm done. This, guys, this is the average between x1 and x2. This minus b over 2a. What is b and what is a? They are the coefficients of my quadratic equation. And I don't know if you remember this from junior high. Your teacher telling you the vertex of the parabola is located at minus b over 2a. Well, this is the reason why. Okay, so this point has as x coordinate that specific point is minus b over 2a. And clearly, since this point is right on top of this one, they're gonna share the same x coordinate, right? That's very simple to see. So also the x coordinate of my vertex, I don't really care about this point, but it helped me found the x coordinate of my vertex. So now I know that the x coordinate will be minus b over 2a. You see, we have found the x coordinate. And in order to find the y coordinate, which is the one that I have to put in here, it's actually very simple, guys, because you have to understand that you're talking about a function. Let me clean this up a little bit. Let's erase this line, this. We don't even need this point. Okay, let's place it there. And so now, if the x coordinate of this point is minus b over 2a, the x coordinate of my vertex, all I need to know in order to get the y coordinate is get this number, right? This number will be the y coordinate of this point. And since you're talking about a function, guys, all you need to know is to evaluate the function in this value of x, right? Which is going to be the function evaluated in minus b over 2a. You see? in order to get this function. If this point in x is minus b over 2a, then when you get the evaluation for the function in that precise number, you will get the x coordinate, this one. And basically, this is how you get the vertex of any quadratic function. That if you know its coefficients a, b, and c. If you notice, the coefficient c doesn't even play a role in this. So let's put into practice this formula. Suppose that I give you this quadratic function, x squared plus 4x minus 6. Okay? And even if we don't have a graphing calculator or that stuff, we can get the coordinates of the vertex the x coordinate and the y coordinate by following the formula, right? The x coordinate, let's call it vx, the x coordinate of the vertex, it's going to be equal to minus b over 2a, and the y coordinate of my vertex will be the function, this function, evaluated in such x coordinate. So let's do it. How much is b? It's 4. So I'm going to get minus 4. How much is a? It's 1. So 2 times 1 is going to be 2. And this is minus 2. You see? So the x coordinate of the vertex is minus 2. And now, if I evaluate the function, this function, in this number, in minus 2, I'm going to get the y coordinate. So let's do it. Let's evaluate the function in minus 2. I'm going to get minus 2 to the square plus 4 times minus 2 plus 6. This is going to be 4 plus minus 8 plus 6. And this will be 2. Right? Yes. So we have found the coordinates for the vertex for this particular function. You see? So it's actually pretty simple. So you have to memorize this, and now you know where this formula comes from. The minus b over 2a, and the y coordinate is the function evaluated in such coordinate. Now you understand why this is so.